Objective 1 is deciding whether an ordered pair is a solution. We're going to start off with a system, which is 2 or more lines, and we're going to determine whether 3, 9 is a solution of the system. What this means is I'm going to put 3 in for x and 9 in for y. And if this is a solution, then each of the statements will be true. So 5x minus 2y equals negative 3. I'm going to put the 3 in for the x and the 9 in for the y. And then I'm going to do the math. And if I have a true statement, then that means that 3, 9 is a solution for the first equation. And now we have to check the second equation. So our second equation is y equals 3 times x. I'm going to take the 3 and put it in for x. I'm going to take the 9 and put it in for y. So I've got 9 equals 3 times 3. 9 equals 9. And because both of these are true statements, 3, 9 is a solution. Determine whether 3, negative 2 is a solution of the system. We have 2x minus y equals 8, and we have x plus 3y equals 4. This is x, and this is y. So 2 times 3 minus negative 2 is equal to 8. 6 plus 2 equals 8. And that checks. Now we're going to plug the same point into our next equation. 3 plus 3 times negative 2 equals 4. 3 minus 6 equals 4. Negative 3 equals 4. And of course we know this isn't true, and so this is not a solution to the system. Our next objective is to solve systems of equations by graphing. The first equation I'm going to write in slope-intercept form simply by adding 3x to both sides. So I start off with negative 3x plus y equals 10. Add 3x to both sides. And you get y equals 3x should be minus 10. So I'm going to graph that now. I start off at negative 10 and I go up by 3 each time to get a line that looks something like that. And now I'm going to graph x minus y equals 6. And I'm going to use standard form. I'm going to use the x and y intercepts. So I've got x and y. If I set x equal to 0, then I have negative y equals 6, or y equals negative 6. If I set y equal to 0, I have x equals 6. So my two intercepts are 0, negative 6, and 6, 0. And as I graph that, I've got a line that looks something like that. And you can notice where the intersection is right there. And that is the point 2, negative 4. Now what I need to do is check this point in each of the equations to see if it's really a solution. So I have negative 3x plus y equals negative 10. I'll plug the 2 in for x and the negative 4 in for y. Negative 3 times 2 plus negative 4 equals negative 10. Negative 6 plus negative 4 equals negative 10. And you can see that that does make sense. So 2, negative 4 is a solution for that line. Now I have to check the next one. X minus y equals 6. So 2 minus negative 4 equals 6. 2 plus 4 equals 6. And you can see that that is a solution too. The answer to this question is 2, negative 4. A system of equations that has at least one solution is said to be a consistent system. A system that has no solution is said to be an inconsistent system. Example 5 says solve the system of equations by graphing. Incidentally, if you're looking for example 4, it was exactly the same example as example 3, so we didn't do it. So example 5 says solve the system of equations by graphing. I'm going to graph the first equation, and if you look at it, it's in a great form. We could use the x and y intercepts to graph this very easily. And then I'm going to, for the next one, I'm going to divide both sides by 2, and then I will have y equals 3x, and I can choose values for x. I have 3x minus y equals 6. If I let the x be 0, then I have negative y equals 6, y equals negative 6. Then I'm going to find the x-intercept by letting y equal 0. So I have 3x minus y equals 6 is my original. Let y be 0, 3x equals 6, x equals 2. I have 0, negative 6, and 2, 0. So 0, negative 6 is here, 2, 0 is here. And there's my line. The next line that I'll graph is 6x equals 2y, and I've already solved for y. I have y equals 3x. So I'm just going to use a table. And I'm going to put in negative 2, 0, and 2 for x. And I get out negative 6, 0, and 6. So I have the point negative 2, negative 6. And then 0, 0. And then 2, 6. And notice what's true about those two lines. Those two lines are parallel. There are no solutions to this. And we call this an inconsistent system. When the graphs of two linear equations in a system are different, we call them independent equations. When the graphs of two linear equations in a system are identical, we call the equations dependent equations. We're going to graph the system of equations and solve. We're going to start off with 3x plus 4y equals 12. We're going to use x and y intercepts. So if I'm looking for the x-intercept, I let y be 0. So 3x is equal to 12, x is equal to 4. And I have the point 4, 0. For the y-intercept, I let x equal 0, and I solve for y. So I have 4y equals 12, y equals 3, and I have the intercept of 0, 3. And it looks something like that. 9x plus 12y equals 36. I'm going to look for the x-intercept first. That means I set y equal to 0, and I have 9x equals 36, x equals 4. That gives me the point 4, 0, which I already have graphed. Then I'm going to look for the y-intercept. And I let x equal 0, so 12y is 36, and y is 3. and I already have that one graphed. So when we graph this line, we're actually getting the same line that we just graphed. These lines are the same lines. There are many solutions. These are called dependent equations. And the way I write the solution is x comma y, which is a point, such that I can choose one of them to write. I can choose either one. 3x plus 4y equals 12. When graphing the two lines associated with the two equations in a linear system, three different situations can occur. You can get one solution, you can get no solutions, and you can get many solutions. With one solution, we call this a consistent system, where we have at least one solution. The equations are independent equations. In the second instance, we have an inconsistent system where we have no solutions, but they are independent equations. In the third situation, we have a consistent system because we have at least one solution, but they're called dependent equations because the graphs are identical. Our third objective is to find the number of solutions of a system without graphing. The best way to do this is to put the equations in the same form. So I have 3x minus y equals 6. And if I put this into slope-intercept form, I'll be able to compare it when I put the next one into slope-intercept form. I'm going to subtract 3x from each side. I've got negative y equals negative 3x plus 6. Now I multiply each side by negative 1, or I divide by a negative 1. So I have y equals 3x minus 6. Now we'll move on to the next one. We start off with x equals 1/3 y. I'm going to solve for y by multiplying by the reciprocal of the 1/3. On the left-hand side, I've got 3x. On the right-hand side, I have y. So I can rewrite that as y equals 3x. Notice that both of these equations have the same slope. But the intercepts are different. The one on the left is 3x minus 6. The one on the right is 3x plus 0. If I need an intercept, I can add 0. And so these are parallel lines. They have no solutions. Example 8 says, without graphing, determine the number of solutions of the system. Again, I'm going to put them in slope-intercept form so I can easily see what the slope is. So I start writing it down. I'm going to subtract x from each side. Then I'll divide by 3. And my slope here is negative 1/3. Now let's move on to the next one. We have 4x minus y equals 10. Solving for y, I subtract 4x from each side. I have negative y equals negative 4x plus 10. Now I'm going to divide by a negative 1 on each side, and I have y equals 4x minus 10. The slopes are different. They are not opposite reciprocals of each other, so these will have one solution.